Next we have Holger Brunst. Holger Brunst, a good friend of mine. He comes to us from the Technische Universität in Dresden. Holger primarily deals with HPC software that is more than 20 years old. He's rather a performance person than a Lustre person. In the early stages of his career, he used to be the guy behind the probably known Vampire performance visualizer doing the real work. Today, he's mostly bugging a team of young people doing the real work with his ideas on tool usability, future perspectives, and needs. Ladies and gentlemen, Holger Brunst.
Okay, today I have the pleasure to talk to you about work that we recently carried out, and it's actually ongoing in the scope of this project. So it's funded by the NEXTGenIO project, funded by the EU, and which is why I start off with some motivation. I just quickly walk through it. So this project addresses future I/O issues. It's funded with a decent amount of money. You see all the partners on the project on this slide, and it's running for 3 months, and within this scope, University of Dresden is actually in charge of doing or dealing with tools that support I/O monitoring and visualization, which is our main job, I would say, and our specialty. So the key thing in this project is that we are going to have a system that is equipped with non-volatile memory, which is somewhat new, especially to the tools guys. So far we hadn't to deal with that. So in the end we will have much more memory at hand, which is going to be somewhat slower than DRAM, but presumably much faster than SSDs that we have today. The memory will be on board, on each board essentially. And the question in this project is actually, how is this going to help people doing I/O, in particular with file systems like Lustre and things like that. So, and our job is to help those people to actually benefit from such a system and from such an architecture. And as I said, in this scope of this project, the architecture is going to be developed as a whole, and we are dealing basically with I/O performance issues. So what we are going to see is basically 3 usage models. The first model is going to be basically, we're going to use this memory as an extension of the main memory. Data is volatile, nothing much more different than today probably. When it comes to the storage model, we have now basically the memory as persistent block devices, which is very much like SSDs, so I/O. The application direct model is, well, a mixture because it maps persistent storage directly into the address space, and I would say this is somewhat more like a memory map file essentially. And we want to cover all these usage models, we have to cover all these usage models in our tool. That's the tricky part for us. So overall, what is probably different compared to the systems that we have at hand today is that the memory hierarchy over here, is this working? Yes, it is working, is becoming much more complex. So we have additional layers here, and we want to have these layers represented in our tools, which is our job. So when it comes to using the storage, which comes to my mind immediately, basically, well, usage as a traditional Lustre file system, global file system, that's pretty easy because this way people can basically keep their applications as they are, fine. Question is whether this way is going to help them to benefit from the availability of non-volatile memory. That's not clear to me yet entirely. So, another thing which is somewhat new on the scene, and also to us from the tool side, is using the memory as object stores. So we see a different way of using and doing I/O. And here, from the tools perspective, the tricky thing is, how do we make those object store accesses visible to people. So far we had files, that's easy. And we know how to get this back to the users, how to do the mapping to the application when it comes to the performance data graphically. With object stores, it's more complicated. And we'll see how that is going to develop, because that's a scenario which has a Lustre file system on the bottom. We heard about that yesterday, but it's not directly visible to people from the object store perspective. Another important thing is in this scope that in the past we typically had one HPC application, fine. Today what we see is that people are coming up with a bunch of applications that are chained, that are exchanging data, that are writing files, reading them again, and it's just a mixture of many applications, and doing performance analysis for these kind of workflows is tricky because you want to have the overall picture, and we typically only support a single application run. So we have to deal with that also somehow. In particular, writing things to the file system, getting things back to the application, having multiple jobs that are dependent on each other, and how do we visualize that so that people actually can get a clue what's going on? And especially, how do we merge the data? I mean, we're collecting a lot of data for such applications and workflows. And the question is, how do you merge that within the scope of the file systems that we have at hand? Tricky thing from a tools perspective. So when it comes to the tools, what are the main objectives that we are facing in this project, but also in the future from my perspective? Well, first of all, what we want to see is the interdependencies that we have on the multiple I/O layers. It's just not one layer, it's a very complex hierarchy. So we really want to see all those parts of the hierarchy that are participating in the overall performance. Next thing would be the workflow visualization that I mentioned earlier. And of course, the fact that we have this huge amount of non-volatile memory at hand, which can be persistent, leaves the question to me, how can we actually benefit on the tool side from this availability? The tool that we are producing is somewhat memory dependent, so we really need also memory to get going. And this leaves quite some opportunity to us actually to also benefit from that. I added this slide because last time I was so thrilled by the new opportunities that we have that I basically forgot entirely to mention the tools that we are developing. Should not happen this time. So this is all taking place in the scope of SCORP and Vampire, which is basically SCORP, the monitoring, the collecting side, and Vampire, the visualization side, just to mention that. Okay, on the I/O layers, what are the information that we are interested in? What are we tapping typically? So this is from bottom up, top down. On the I/O layers, we have, of course, the Lustre file system. We have the client side. We have the server side. We have the kernel that we can actually tap for certain information, certain statistics, numbers. We can instrument the POSIX layer. That's what we're doing as well. We can instrument the MPI layer. We can instrument abstraction layers like HDF5 NetCDF or parallel NetCDF. And the goal is now to combine all this data into one picture, one view, and show interdependencies and effects that are resulting from applications and the way people constructed and designed their applications. When it comes to Lustre I/O performance data, what are we interested in? First of all, we want to see, and that's a difference to the profiling approaches that we've seen before, we really want to see event data. So whenever something is done regarding a file, read, write, or open or close, we want to record those individual events, at least a great deal of them, probably not all of them, might be too many. And of course also we are interested in aggregated numbers that we can get from systems counters and anywhere in the system how they are created. So on the client side, that's fairly easy because we have a POC file system that we can access from a PAPI components abstraction layer. We are familiar with that from HPC, so SCORP can basically do the job out of the box right now. On the server side, things are a bit more complicated. By the way, this is all done, or this can all be done in user space and without kernel rights and root rights, I mean. So that's quite user-friendly in a sense. On the server side, it's a bit more complicated because you need some kind of infrastructure to collect all that data. you need a database, you need some sort of mapping to get this information back to your application, and that's the trickier part. It can be done, but it's not so easy to convince people running the real systems to basically maintain such an infrastructure. So, which is why we typically reside and stay on the client side. It's just, yeah, a way how practical things are or not. I also said something about non-volatile memory, so I don't want to spend much time on this here because it's not really I/O in that sense. There are libraries that help us to basically keep track of what's going on directly on the non-volatile memory, and the NVM library, for example, can tell us about allocations, freeze, and things like that. We get information about health status, also read-write statistics, things like that, but it's not probably the focus here relevant for Lustre. A lot of facts so far, and the strength of our tools is visualization. So basically, from now on, I will stick to the visualization that we are thinking of. What you can see here is basically how our life works, what we basically do, and what we provide to users. And it's typically a time-based picture. So you see the application over time, from left to right, that's the time axis. And the colorful boxes and the yellow boxes, for example, they represent individual file operations as they happen over time. On the lower side of this picture, you can actually see statistics aggregated over this particular time. Whenever you change the time interval, the fact that we are dealing with events helps us to recalculate those stats over time. And of course, you can also derive pictures like that show you bandwidth numbers and things like that, how they develop over time. So that's pretty straightforward. That's business as usual for us. Nothing new here, I would say. Just that we support additional layers. When you do this approach, you can, of course, also derive I/O summaries and totals, like we've seen before. So I'm talking about IOPS, IO time, the sizes that are aggregated over time, and bandwidth, simple. But typically when it comes to application developers, they really want to know what's happening here, what's going wrong from a file perspective or from an object's perspective. So this is how we think that the world should look like from that detailed point of view. So what you see here is basically an overview of individual files and how they have been accessed over time and how much time is spent in those accesses. And of course, the statistics can also be switched to bandwidths and latencies and things like that. Okay, traditionally, what we show is how individual processes or MPI ranks or threads access files over time, which is depicted above. So basically, you see over time a single process or multiple processes. The rows are individual processes and how they access the file system over time. That's what we do for quite some time already. We realized that sometimes it's also relevant to change the perspective to the resource, actually. So when it comes to individual files or standard I/O, you would like to see, okay, when are we performing accesses to individual files over time? So we are now looking at the data from the file perspective, no longer from the rank perspective, I would say. And you can create pretty nice access patterns with such views where you can actually see precisely over time how individual parts of the data structures on disk or on the file system have been accessed. Okay, this is basically the charts that we have so far. And now I would like to show a real example from actually work that has been carried out here at IU. So this is really a practical thing. So how did it start off? It turned out that actually a very straightforward application, single application that was single-threaded initially, was parallelized in a somewhat easy manner, I would say. And it turned out that with this simple application, the Lustre file system on site really suffered a lot. So this application produced huge amounts of I/O, and it was not really clear why it would do so, because I think the developers agreed that the I/O demand should not be that high. So the question was, what's going on there? And this is where tools can come in handy. And if you look at a phase profile over time, you can actually see that on the upper part, the application runs through phases where computation is followed by I/O, is followed by computation, is followed by I/O, and so on. And on the lower part of the picture, you can actually see that it has on average, a single thread has on average something like 100 megabyte of I/O bandwidth, which is not a whole lot, but when you scale that up, or when this was scaled up to many threads on multiple nodes, that would, in the end, well, be a problem. And from this perspective, there isn't much to say actually about the application. So what is the cause of this aggregated amount of I/O? That was not really clear. And that's where, well, the work started for me, because providing details can make a difference here. And what you see here basically is that I picked out one of those phases, so I now was able to jump into very small detail of the application. And as I said, this is repetitive behavior. So one of the things that came into my eye immediately was that, first of all, what you can see here, probably, I'm hopeful that this is detailed enough for you on the screen, that it turned out that this application was using NetCDF for abstraction. And looking at this NetCDF calls, for some reason, which is not entirely clear to me, because I'm not a NetCDF expert, with the usage pattern or with the data structures behind, a single call of get me some bytes of data via NetCDF get verifloat resulted in a tremendous amount of POSIX reads on the file systems, although it was just in the order of 1 or 2K data that was read. But looking at the instrumental application like you see here, it turns out when you see both layers, the NetCDF layer in orange and the POSIX I/O in yellow, and those arrows actually show individual operations, that one single NetCDF call actually triggered this huge amount, and this is repetitive behavior. So this is done over and over and over again. And this should clearly not be the case. Looking at the statistics that come with this portion of time, it turned out that actually from this one single access loading around 2K results almost 100 times of data access on the POSIX layer, which is a pain. So this should clearly not happen. And doing that over and over again obviously stresses the file systems without any real need. So we've been working on that. And so what people basically did was, first optimization was, because the code was not supposed to be modified, that's the problem, was to stress not Lustre anymore, but in this particular case it was possible to outsource this to basically a temporary file system. And with doing that, the problem could be somewhat solved. Another issue that was also revealed during my taking a closer look at things was that actually, even with those many calls that we've seen before, the I/O demand that was reported to me was way higher than what I saw in the tool initially. In the middle, you have this ping graph, and this is actually the picture or the bandwidth demand as it is calculated by the tool when looking at the POSIX I/O layer, and also the NetCDF layer, by the way. And this really did not match what I was told by administrators, so I wondered, whoops, well, why that? And so that's where I started to incorporate more information into the trace. And I basically used the kernel in this particular case to get also numbers from the system's perspective. And it turned out that, yeah, there were actually phases in the code, which is depicted in the blue graph, that were not covered by our instrumentation. So it turns out that at certain phases in the code, presumably here the cases where, or the situation where files have been opened, we had a lot of bandwidth requirement as well. And this might be, well, very intuitive to you, but it was not to me at the time. And it's actually happening again over and over. This is presumably the prefetching thing that goes on when you open a file. And the fact that this code is coming from a serial platform and is doing those open and close things just like they don't matter, deals, and obviously it's different files each time, and this basically keeps on the system layer, the system prefetching data over and over again, and this results in, yeah, the high I/O demand and part of the I/O demand. And what was the solution to that? Pretty simple. Basically avoid the open and closes over and over again. And fortunately, that was possible to carry out, and which is what people did here. But without actually looking at all those individual layers from the application perspective, the developers basically told us, no, we are loading just a few kilobytes. Should not harm the system at all. But if you look through those individual layers, you can actually convince people what's going on there and what they can actually do about that program, and the fact that they actually have an influence on layers below them, and it's important to do things right for HPC systems or for very scalable systems, which I can convince them much easier with such pictures than with just the numbers. And this is, I think, one of our strengths. Okay, let me summarize. So within this project, we are working on a full hardware and software solution. We are addressing the software solution. I'm lucky that we are funded in that respect, and that almost half of the money is spent actually on software. This includes Lustre for sure. So Lustre is definitely part of the entire system architecture, which is true for the operating system side, but also for the performance side. In the scope of my work, we basically focus on considering the complete I/O stack. That's, I think, very important to get the entire picture, not just one layer. It's hard to explain things from just one layer. Within that effort, we incorporate a new set of I/O paradigms, like accesses to NVRAM, things like that, into our performance visualizer. And of course, we also study implications of NVRAM, although that's not relevant here. I'm pretty optimistic that we can actually use this architecture and also our tools to, in the future, reduce the I/O costs, and also to find new usage models for HPC and HPDA to actually make use of those I/O capabilities that are on the horizon, coming with these kinds of, well, different I/O devices, I would say, although it's not per se I/O devices. And having said that, I would like to conclude my presentation, and in case of questions, I'm willing and happy to answer them. Thank you. Any questions? Up front?
Aren't we glad that they're working on the ceiling roof next door? It's so nice. One thing I don't have control over. Sorry about that.
I'm just curious to know that, can I try a performance visualizer? Can we try that? Download
sure, and try. Okay, well, the thing is, this is partly software under development. So of course you can try SCORE-P and Vampire, but part of the stuff that I showed here is not yet on the release branch. So you can try it if you ask me, and I will provide you the software for that. It's going to be in the release soon, but it's not yet there.
Sure. And the second thing is, how helpful will that be if I run it on my VMs? I don't have NVMe and those kind of hardware. So.
I would say it would, first of all, as we don't do any fancy things on kernel levels and things like that, so it's also going to work on your NV and on your virtual machines. And I have no idea how your problems look like, but the fact that we basically reflect what's going on in the application over time, I'm sure that it's going to provide you insights that you haven't seen before. So this is typically my experience when I do things together with application developers, that they basically are surprised by their own application and what it's doing compared to what they think it's actually doing.
In your example, where you showed that there was this system traffic that was coming from the prefetching, and you said initially you didn't see that, and then you added something. How are you capturing those statistics?
This particular case, well, the direct way would have been to use the Lustre counters on the client side, which reflect basically the Lustre perspective. Here in this particular case, that did not work, I have to say. As I said, this is work in progress, and I used the R usage counters that I can get access to from the kernel, basically, which is somewhat indirect, but normally there would have been the Lustre information there as well. This is just, I just have to be honest, for this particular slide, I did not use it.
Any other comments or questions?
Nope. Thank you.